So Robert is a principal systems developer, and let's see. You work for Schwann's Home Delivery, providing business solutions with web technologies. He's a Microsoft MVP, a Progress Ninja with Fiddler, an ASP.NET Insider, a Pluralsight author, and a third-degree black belt in Taekwondo. Robert regularly speaks at national and international events. Welcome, Robert.
Thank you. So we'll jump in and get started. So like we said, we're going to talk about Cryptography 101. I'm an ASP.NET developer, C#, obviously web. The nice thing is all of these things apply across languages, frameworks. It's more important you understand the concepts, the algorithms involved, what not to use, approaches you want to take. I just happen to have all my examples web-based, C# and with .NET 5. I have the slides and the code available. So I have both a .NET 4.8 version and .NET 5. They're very similar. I'll talk about a few parts where they're different as we go through. Won't spend a lot of time here. We already went through an intro, but I wanted to point out that's my Twitter, my email, and my blog. And as I said, I'll have a link at the end that shows that again and also has a link to the slides and the code. A little bit of background. So cryptography is the science of keeping messages secure. And if you ask people why would they want cryptography, most people think about confidentiality. Historically, you think about cryptography and being able to protect data from being read. There's also other goals. So integrity is important. We want to make sure that data has not been modified. We use it for authentication, being able to identify and validate a user. We also want non-repudiation, which just means a sender cannot deny later that they sent a message. In .NET, all of these classes we'll find will be under system.security.cryptography. And it'll be important as we look at techniques to come back to what your goal is, to know that you're using the right techniques. I see a very common thing where people misunderstand hashing versus encryption, for instance, and they're not sure which one to use, and they're misapplying because they're not understanding what their goal is and what they should be using for that particular goal. So we'll refer back to that throughout the talk. Lots of considerations when you do cryptography. Again, what's your goal, I think, is the most important. Primary threats. So you need to sit back, and we're going to go through and see some history about how people did what they thought was secure, it was broken, how they reacted. It's important to think about your primary threats. I'm an e-commerce site, so my website sits on the open internet. Obviously, we have firewalls, web application firewalls, all of that sort of thing. But I need to think through what are the threats for my environment where this will be deployed. So obviously, in transit, I want to use HTTPS for sure. Everyone should be. I also treat the web servers like they're compromisable. On any given day, I could have a 0 day for my web server and someone could own my web server. And that's my perspective. And that will show what all the threats here are. People could look at my config files. They could dump memory. They could see things that are stored in .NET strings. They could modify pages. They could reverse engineer assemblies. I did capture the flag the first time last year, and it was very instructive for me. I've done security before from the protection side, but being an attacker, I knew about the attacks, but actually going through and using attacks to transfer money on this simulated banks and stuff, you really have a different lens into how people will attack you. So it's really important to look at security from that point of view. How will people try to break that? And we'll look at that as we go through. I have company security policies I need to deal with. I have regulatory compliance like PCI. So all of this comes into play about how I should use cryptography and what the rules around how I should use it. I want layered defenses. So I want to have not just one thing broken and everything is over. You need to consider how many are enough, right? I mean, if I wanted a totally secured system, I'd power it off, put it in a lead box in the corner. Not really going to help me sell things online, right? So I need a balance of what I need from a security perspective and what the risk is compared to what the business benefits are. If you take nothing else from the talk, please don't write your own cryptography. So there's been lots of history around people see algorithms, they're concerned that they're out in the open and people have access to them, so they think if I just wrote my own and no one knew what it was, it'll work out great. There's lots of very good cryptographers. I'm going to reference Bruce Schneier later in the talk in one of his books, and he's done tons of cryptography work. And he's also done things that were mistakes. You need to work together in the community and be involved in the community. Just please don't write your own. You'll see how easy it is to leverage, in my case, what's available in .NET. Take advantage of what you have that's been vetted and tested by others. I want to mention how .NET algorithms are implemented. So I gave a link here. It wasn't easy to find in the past, but you'll see some of the classes will have particular suffixes. So you'll see managed or CNG or crypto service provider. In the .NET framework world, those were meaningful. So if you saw something like AES managed, that meant it was the AES algorithm, but written in managed code. So IL, likely C#. The problem with that in those days was that was not FIPS compliant. So if you did government work, it mattered that you didn't use the managed because that was not FIPS compliant. It turns out in .NET Core and .NET 5, all of these suffixes don't matter anymore because they just wrap operating system libraries. So just be aware it may or may not matter to you depending on how you are going to build and deploy. The other thing to mention, I wanted to point this out, if you're doing cross-platform Core .NET 5, you need to be concerned about whether a given feature is available on a platform. So you may be able to use it to build, and then it turns out when you go to actually deploy, so I'm primarily on Windows, I might do all my development assuming that this class will be available on Linux when I go to deploy. And if I wait till the end, I may deploy over there and find out it's not actually available. So check out that documentation up front to make sure what you want to use is actually going to be available on a given platform. Let's start jumping into foundational techniques now. So the first one is hash functions. These are a one-way function. It's easy to compute, but hard, hopefully, given the algorithm, nearly impossible to reverse. That's what a hash function is. So if you look at the picture, I have some text here on the left-hand side. I'm going to compute a hash of it. It's going to give me a fixed size. So depending on which hash function I choose will determine what that size is. It doesn't matter how large the left-hand size is, that hash will always be that fixed size. People often call this a data fingerprint or a digest. It basically represents this whole thing with this value. And if you have a good hash function, changing a single letter in here will have what's called an avalanche property, that it will substantially change what the hash is. So just changing one thing is going to drastically give you a different hash. Why do we want to have this? We're going to use this for integrity and authentication. Within .NET, the hash algorithms, the base class is called hash algorithm. I've listed ones that are available in .NET, but you shouldn't use. So MD5, if you follow breaches, MD5 has been broken for a long time. It's not safe to use. If you run into a system where you say, I think I need this because of legacy compatibility, really challenge the need for that compatibility and making a change, because MD5 is essentially completely broken. Also true for SHA-1. So SHA-1 was deprecated for PCI compliance a few years ago, so it is also considered compromised. I'm going to focus on SHA-2 family of algorithms, and in .NET there's going to be 3 different ones depending on the size you want for the fixed output. So this is 256 bits, 384, and 512. I'll mention there is a SHA-3. So when SHA-1 was broken, NIST decided to have a competition and said, we better start getting ahead of the game in case SHA-2 got compromised. We want to already have an alternative. So they ran a contest, and I think it was chosen in like 2015. So there is a SHA-3 family of algorithms, and what they wanted was them to be implemented in a completely different way than SHA-2. So those are available. I don't list them here because presently they're not available in .NET. Company policy, personal philosophy. I'm not going to go find George's blog on the web, right? And George wrote an implementation of SHA-3 in .NET. That's not something I'm going to use on my production systems, right? I need to use things that I know are trusted and vetted. I'm using .NET. I could go look for third-party libraries. SHA-2 is still considered completely safe. I'm just going to stick with SHA-2, and that's what we're going to show throughout the talk. There's also what's called key hash algorithms, and so we'll talk about why those are needed, and I'm going to focus on the SHA-256, 512, the HMAC variants of that. So let's take a look at what code would look like. So I've got a simple example here. I've just got some plain text, and I've got what it hashes into here represented in hex. So I just wanted to see. So I happen to be using Razor Pages. That doesn't matter. I'm not going to focus on that at all for this talk. I'm just going to focus on the cryptography. So you can see here's my plain text, and it's a string. What you notice in .NET and most cryptography libraries is they don't deal with strings. They deal with bits. So unfortunately, we're all used to using strings all over the place. So we're going to need to be able to convert from a string into bytes. You'll notice the classes here. I'm going to use SHA-512. We'll talk about sizes and difficulty and things later. I'm using SHA-512. I just wanted to show you these other suffixes. Again, I'm in .NET 5, so these are pointless, so I'm just using the straight up SHA-512. So my first hurdle, again, I need to change that string into a byte array. So there's many ways to do that. I just need to encode it. There are several ways. UTF-8 is very popular. If I'm only working on my own system, it doesn't matter what I pick. I just need to use the same thing throughout. If you're working with a partner, this is something you're going to have to talk about, is how you're doing your encoding. So I'm just going to use UTF-8. It's in the encoding library. Once I do that step, I'm going to have a byte array. Now I can use the compute hash, and I'm going to get back a byte array here on the left-hand side. So that's all I needed to do to compute the hash of that string. We talked about sizes. I'm not going to do this here, but if I were to uncomment this much larger plain text, the resulting size of the hash will still be the same. That doesn't change. That's driven by the 512. I want to show this byte array on the web, right? I need to change it back into a string. So there's also several ways to do this. I like to use hex. I'll also show you base 64 later. The bit converter class in .NET will take each byte, convert it into hex, and put a dash in between it. So this line just does the bytes into a hex string and takes the dashes out, which gives you the view that you saw here. Okay? That is hashing. Why would I want to do this? So I try to show you practical examples throughout the talk. I'm sure you've been to websites. You look at the URL, it has customer number equals 123, right? Guessing that's a sequential number. I could go to the URL and change that to 124, and suddenly I'm looking at someone else's data. So the issue there is I don't care that you see necessarily that the customer number is 123, but I do care that you don't tamper with that number. I don't want you to be able to change from 123 to 124. I want to protect the integrity. So we're back to the goals. The integrity of that query string. I'm going to do that using a hash-based message authentication code. So it's a hash, but it also will have a key. So the idea is when I construct a link, I'm going to compute the hash on the server of what that link should be and what its hash value is. I'm going to append that onto the URL. Now, when you come back to my site again, I'm going to take what you sent me as a query string, hash it, and compare the two hashes. That's how I'm going to tell if things have been tampered with or not. So let's take a look at what that code would look like. And I'll just show you the web version first. So I've got a link here. I'll click it. I'm on a page. It says, hey, you have A equals 1. If you go up on the URL, I've got A equal 1, B equals 2, C equals 3. So again, that's my query string. These values are such that I don't care if you see them. So it's not a confidentiality issue. It's an integrity. What I don't want is I don't want you to come up here and change this to 2. Hit enter and be able to see anything. So you'll notice on the end here something that should look familiar. This is a hash of the original query string. So again, thinking like an attacker, I'll come out here and I'll try to change that to 2. I'll hit enter. I'm going to give you some warnings throughout the talk. Don't ever do this in production, right? Don't show exceptions like this. I'm doing this because I need to demo this for you, and you want to be able to see what the actual error is. In this case, the query string hash values don't match. If I were to show that in production, I'm telling an attacker they're using hashing, and now they have a better idea of how to come and attack. So again, the query string hash values didn't match. Maybe if you don't know a lot about hashing, you'd think, I can just guess, right? So I'm going to try to change that. Still doesn't match. Well, maybe the developer didn't do a good job. And if there isn't a hash sent, maybe it'll just go through. These are the kind of things you need to think. Again, be an attacker, try some things, make sure you've covered your bases. So let's look at how the code looks. One thing you'll notice, I used to be able to create normal hyperlinks in markup. I can't do that now. I've got to use code to calculate this query string. So here's what I want for a query string. I've just written a common function. This is pretty typical for your company. You're going to want to be able to compute a hash, pass it some data. I pass in whether I want to get back hex or base 64, and I have a parameter whether I want to use a key or not, and then some other data we'll talk about in a moment. So why would I want to use a key? So if you think like an attacker again, if I were attacking this and I saw it used hashing, I would go figure out the size. So if I went and ran that again, if I figured out this is a hash, I can figure out how long that is, and I can determine there really aren't that many hash functions out there. So I'm going to use the same thing you would use. And I'm not going to do the whole process here, but if you look on the code I'll give you, there's a hack tamper proof. I have access to the same hashing you do, right? If I can do a SHA-256, I want the value to be 2, I would just compute a hash of what it should be, right? So let me run it. This is what the hash would be if I use the value 2. Now, if I go back to the original example, I can change a equals 2. I'd be able to paste this hash and be able to circumvent all of you. Talking about layered defenses again, you know, normal people aren't going to do this. It might stop simple hackers by just using hashing alone, but I want to protect against as much as I can. That's why I'm going to use that keyed algorithm. So the idea with a key is I'm putting one more hurdle in place. Not only do you have to know the algorithm and how to calculate, but you need this secret key. Again, warning, don't store your secret keys in strings, right? That's going to be in version control, everything else. Again, for the demo, I need to give that to you. We'll talk briefly about key storage later. That's actually the worst part of cryptography, is how do you keep secrets. But again, if I didn't use the keyed, now that I did the keyed, you need one more thing to compute a hash. So I've made it harder. The average attacker, I told you that people could own my web server. So if someone was really good and I was doing this, that would be in my assembly. Someone could reverse engineer it and get it. But if I drew a funnel, the number of people that can do that is very much smaller than it would have been if I didn't do that. So that's a good place where you can see hashing makes sense and it has a practical use that people should use on websites. Where's another place people use hashing? Passwords. So I used to do research a long time ago when I was in college on security and password security. Unix back then, when Unix was created, they basically said, we need a way to store passwords. Okay, how should we do that? And they considered encryption for a while, but we'll talk about why there's some issues with using encryption. They looked at hashing and said, hashing is brilliant. What we'll do is if you give us your password, we'll hash it. We'll store the hash of your password in the Etsy password file because we know it can't be reversed. If it's a good algorithm, someone can't take that hash password and get back to where I was. So they said, that's great, we'll do that. They got a little overconfident, another thing you don't want to have with cryptography. And they said, we might as well let everybody on the system read the password file. Why not? We know they can't reverse it. So what happens is people came in and attacked it and they said, I know I can't reverse that hash, but I could take the entire dictionary, you know, all words in a dictionary, and compute a hash of all of those words. Now I just need to compare my hash to what's in the file. And it turns out back then about 60 or 80% of passwords would be found using a technique like this. So I'm going to show you the code briefly. This would be how somebody would crack. So if I were to create this, I just create a dictionary. I'm just pre-computing some words that I think you might use for your password. So here I would go to an online dictionary. Thank you, social media. These days, if I were aggressively going after you, I'd go after all your social media. I'd know your dog's name, all your pets, kids, spouse, whatever. I'd know where you went to school. I would take all of those things and compute hashes of them. Once I throw them all in this dictionary, I would take the hashed password out of the file, and now it's a simple, you know, does that value show up? And if it does, what was the original word when I computed it? So if we were to run this, Turns out it was secret. So again, I didn't break hashing, I didn't reverse it, but because they didn't think about how people would attack it, there was an avenue to just pre-compute my own hashes, what people sometimes call rainbow tables. So we talk about defenses. I'll call them the good team because I'm on the protection side of this. They said, let's add something that makes this more difficult. So they said, let's add what's called a salt. If we took some random data for each user and stored that, so you take your password, some random data for, let's say, Robert in the file, and compute a hash of that and put that into the password file. They also put the salt on the password file because when I come back and I type my password again, they're going to take that salt, my password, hash, and compare the two again. They thought this is brilliant again, right? This stops people from being able to do the dictionary attacks. What it did actually, it made it harder for an attacker to attack the entire file, right? Because now if I want to pre-compute a bunch of hashes, I need to do it with Robert's unique salt. So I could do that, right? I could go compute that. But if I have to do that uniquely for every user, it just makes it harder for me to attack. So it was better because it made it harder to attack the whole file at once. It didn't make it any harder to attack a single user. So I would go look for admin if it were me, take their salt and pre-compute everything against theirs, because if I got the admin account, I have the rest of you, right? So it's better, not perfect. The idea again would be to add something else on the server. So I'll show you what this code looks like. I'll talk about how to generate salt here in a bit, but I've got, for this example here would be some data. I pre-generated some salt specific to you as a user. That salt would be stored along with your user in the password file. We were computing hashes before, now we can compute hashes and pass that salt. So now this will be unique. The other advantage of this is even if we both chose password, please don't, as our password, two of us, that won't hash to the same thing anymore. So if you found mine, you wouldn't see who else used the same thing. Adding one more layer on the server, I can also just pass in another secret. So not only will I use salt, I can also store this secret. So again, now I've made it harder. You can't just get the salt. You need to get in and find this secret, which again, I won't just have stored here in a string, to be able to break this, if that makes sense. What do people really do today? None of this, hopefully. Unfortunately, you see breaches all the time that say they used MD5 and they didn't have salt. And so people are still doing these things wrong. But typical today would be to use what's called I'll show you the .NET version, PBKDF2. So these are what are called hash functions that have a work factor. In other words, you want to make it very difficult for the hacker to pre-calculate a bunch of hashes. That's what these algorithms do. If you've heard of Argon2 or bcrypt, those are all examples of this. This is the one that happens to be in .NET, so this is what I'm going to show you. What I do now to do passwords. I'm a Led Zeppelin fan, so I've got I wouldn't have that as a password, obviously, but I've got some salt. This is the class in .NET. The secret to these is this iteration count. So I'm going to look at my current hardware, and I'm going to choose an amount that I'm willing to penalize my normal users of my website. Maybe I say a half second. Once I figure out a half second, I'm going to go run this algorithm on my configuration and figure out how big of a number, how many times do I have to run that hash to get to about a half of a second? Because my goal is I want to make it hard for the hacker to pre-compute a bunch of words. If every time they have to compute a hash, it takes them a half second, it's going to take them a long time to hash the entire dictionary, right? They're at least going to have to limit the choices they're going to use to attack me. So this is standard practice today for password things. Again, the bad news is I'm penalizing my real customer, right? The count I pick here changes what the hash value is. So whatever I choose, I want to get to what is an acceptable trade-off. How long will I penalize every user who comes to my site? And I said a half a second. I come and punch in my password. That hash is going to take a half second before it can compare. So I need to do that balance, right? Life is trade-offs. What's an acceptable amount for this count to make it difficult on my current hardware for hackers to be able to go compute things, if that makes sense. So we're kind of through the hashing part. We've seen some places where hashing is used. Now we're going to jump into what people usually think about for cryptography, which is the confidentiality. There's some terms I use throughout the code that are standard industry terms, so I want to stick with them. The first is your plain text is your original data. Encryption is the process of obscuring that data. When you've done with that, you have ciphertext, which is your encrypted data. Decryption is my process to go back to the original plain text, and a cipher is the algorithm I'm going to use for doing the encryption and decryption. And again, this is about confidentiality. I don't want you to see a secret. The first class of these algorithms we'll look at is what's called symmetric. And it's easiest to look at the picture. I have some plain text. We'll do encryption with a secret key. Once I do the encryption, I have my ciphertext. The decryption is going to use the same key. That's why it's called symmetric. The same key is used for encryption and decryption. When I'm done, I'll have original plain text. So good news is super fast. The problem is key distribution, right? This secret key has to stay a secret or this doesn't work anymore. So if I were to pick one of you at random out of the participant list and I wanted to send you a secret, I have a bit of a problem, right? You don't have a secret key yet, and I don't have a way to send you secrets. So we'll talk later about how to deal with that, but we're going to focus on this first. This is going to be used all over the place for bulk encryption. There's a number of algorithms in .NET. I'm going to focus on AES. DES is certainly broken. Triple DES, if it's not, it's awfully close. AES is the US government sanctioned and what you'll see most often people are using. .NET does its symmetric algorithms are called block ciphers. So what it does is it takes your message, however long your message is, it has a block size. It takes the first, I'm just going to say 16 bytes. It's going to pull that out of your message. It's going to encrypt it. It's going to end up with some ciphertext. It's going to put it aside. I'll talk about some padding and some modes here. Why you want to make certain choices. So you want to pick this and you want to pick CBC. And I'll show you in code why that matters. So what ECB is, it just takes the very first block, encrypts it, puts it aside, goes to the second block, does the same thing. Well, the problem with ECB is if two blocks happen to be exactly the same, so is their ciphertext, which at first you might think that's not a big deal. Here's a kind of a classic example of why it would be. So I've got a picture on the left here. It's true that this is encrypted using ECB mode. So it uses AES, it does encryption, white here gets encrypted to some other value here. But because every white pixel here becomes the same value, you can tell the shape is still visible here. I still learned something because ECB is a bad choice, and I'll show you why. So first let's run this, sorry. I'm just gonna punch in test, decrypt. So if you notice, this is CBC mode. This is the one I recommend. Every time it's getting a different ciphertext for the same plain text. How does it do that? Well, it uses the output. So in CBC, it says I'm going to encrypt the first block. I get ciphertext. I'll use that ciphertext as input into the encryption for the second block. It just adds some randomness to that second block's encryption. And it does that all the way down. So then you ask, well, how does it get it random data for the first block? That's what's called an initialization vector. So when you're in CBC mode and a few of the other modes, the initialization vector is just some random data that seeds your first block of encryption. It doesn't need to be a secret. However, never reuse it. If you reuse the same initialization vector one time to another, you've lost some of the randomization that you could have had. Let's look at what this code looks like. So when I hit the encrypt button, I just wrote a common method called create cipher because it's going to get used for both my encryption and decryption. Again, I'm using AES. I showed you some suffixes here. By default, that's going to use CBC mode, which is what we want. I'm changing the padding mode to the better mode. Again, here is a secret key. Don't store that in your string, but for the demo. So this is my cipher now. So I create a cipher. Once again, as soon as I create that cipher, it will automatically make a random initialization vector for me. So I just wanted to display that on the screen. So here I chose to use another way to go from bytes to string, which is called base 64. So if you see, it's common with base 64 to see it end with some equal signs, double equals. I do the create encryptor. I need to take my plain text string and convert it into a byte array. We already saw that. I'm using UTF-8. And then here's the actual line that does the encryption. And then I have a byte array. I want to show it on the screen again. So I just chose in this case to use base 64 to get it back into a string so I could show it on the web page. So what I want to emphasize is AES is very solid encryption. We've got good modes chosen, and this is not a lot of work, right? Back to why you don't write your own. This stuff is built regardless of your language or framework. You're going to be able to find a library that implements, obviously a trusted library that implements this. That's why you don't want to write it yourself. But that's a lot of power here to do encryption and keep things confidential. So again, why don't I want to use ECB? Stop my web server here quick. Let's see what happens when I change this padding. Instead of using this random padding, if I just pad it with zeros and I do ECB, you're going to see why this is a bad idea. We already saw it with the penguin example, but it kind of helps to show sometimes with code. So if I were to go request this again, oops, sorry, I got to run my web server since I stopped it. Good news is at least I figured this stuff out fast. All right. This is why this is a problem again. If I just have the same plain text, it always ends up the same ciphertext because I'm choosing a poor mode. So yes, AES is solid. Just because someone says they use AES, you need to question what mode are you using? Why does this matter? Well, let's say I send to Battlefield or something, and it's either yes or no every day, right? Attack or don't attack. It doesn't take long for people to see the ciphertext. They don't know and they can't figure out that it is yes, but they can see that the action is something happens and there's only two different values. By using that mode, I'm giving away some randomness that I should be using. And if you're familiar, I'll talk about some of the history later. Enigma was broken because they did things that weren't as random as they could have. If they would have used it in a better way, that wouldn't have been broken. So just be aware with symmetric which mode you're using. I know it's a 101 talk, but I want to mention most people today are using a more advanced technique here, and it's called AES GCM. So what's cool about this one is it's doing both things we talked about. If I just did AES, it's true, it's confidential. You have ciphertext. The problem is people can modify that ciphertext and you won't know. AES GCM is a mode that does what's called authenticated encryption. It's going to use both hashing and encryption together. So I'm just going to run it. You can look at the code later. But if I run this and I type test again, you'll see every time I'm encrypting, I get different ciphertext. The nonce is the equivalent of an IV. The tag is what's important here. So now I'm going to send that tag, the nonce, and the ciphertext to someone else. If someone were to come up here and tamper with this today, there are attacks. If you tamper with just AES, you could get people to decrypt things and have some control over what they would see. By doing this method, the tag, because of hashing, would say, that's been tampered with. Somebody played with that ciphertext. Don't trust it, and we won't decrypt. So I just want to mention that that's there. I want to mention also how you get random keys. So I do have a method in here in the symmetric folder called getBytes. To create a symmetric key, and for cryptography, we talked about why you want randomness. You need to use what's called a cryptographically strong random number generator. So if you've ever looked at like math random, and those aren't really random. You want something that's much more random than that. You need a cryptographically strong random number generator. So this just shows how you can create a key. Computers are never going to be perfect. They can't get true randomness. So I thought it was kind of cool. If you're familiar with Cloudflare, they host a lot of internet sites, reverse proxy and such. They actually have a wall of lava lamps out in California. They take a picture of this wall and the current state of these lava lamps and basically convert it into bits and use that as some of the random input into their random generators. They basically are reaching outside of computer systems into the real world to get some randomness, and I just thought that was a cool way to get it. So that's cool. We said symmetric's fast. It's pretty easy to use. The problem again is the key distribution. I want to be able to pull one of you out of the participant list and say, let's have a conversation. How do we get each other that secret key? The idea with an asymmetric algorithm is, we'll look at the picture. I'm going to get the receiver's public key. So everybody's going to generate a public-private key pair. Obviously, the public one they'll give out, the private one they want to keep secret. So to do encryption, I'm going to take the plain text. I'm going to encrypt using the receiver's public key. Once I do that, I'll have ciphertext, and that ciphertext can only be decrypted with the receiver's private key. So as soon as I do this encryption, I can't even decrypt my own ciphertext here because I don't have this private key. So it's all, be careful, I almost said it. It helps with key distribution, okay? Because now if I have, and this is the key, if I have a trusted version of their public key, this all works great. How do I get a trusted version of your public key? Would I take it from your email signature? No, right? Email is a postcard. Anybody could have changed that. I need to find a place that I have some faith and trust in that I'm getting your proper public key. So maybe your LinkedIn profile, maybe people put it on Twitter. Those use HTTPS if you trust the security of those. So I'm not saying the problem is gone. It's just greatly reduced. If I know that that's your public key, this works nicely. Problem with this is it's about 1,000 times slower than symmetric. And it also, the algorithms that are used and the math they use, they limit the amount of data that I can encrypt. So I'm going to focus on RSA in here and then show you some encryption. It can only encrypt a very limited amount of data. And like I said, it's really slow. So we'll talk about what we're going to do about that in a bit, but you need to be aware of that. So if I look at asymmetric, let's type in test again. I can decrypt that. So that's cool. Each time it's different. Does that actually get implemented? So similar structure to what we saw before. I can pre-generate some keys. So in this case, I have keys, RSA keys represented as XML. So this would be the receiver's key in this case. I have my same create cipher method. I just need to create that RSA cipher, take that key, read it in as the public key. And then this is straightforward. This we did before. I need to change my string to a byte array. I'm going to do the encryption. Be aware there's different types of padding for RSA. Use this one. The PKCS1 is no longer considered secure, so make sure you use that for your padding. I will have bytes for ciphertext again, and I chose to base 64. So again, this is really straightforward to implement using RSA and doing asymmetric encryption. And again, I want to do that because it reduces the risk of key distribution. But again, it's slow. Where would be a practical place I could use this? So I told you I feel my web servers are compromisable. So if I want to take your credit card and I need to store it, I want to store it encrypted. It's not a hashing, right? It's not an integrity thing. It's a confidentiality thing. I don't want people to see your credit card number. So one thing I could do, I could use symmetric encryption, right? But if I did that, I have a problem. Where am I going to store a secret key on a web server that I told you I think people can own, right? That's a bad idea. However, if I did asymmetric, I could create an RSA key pair, store the public key on my web server. Now, as soon as I get your credit card, I can do that encryption using my own public key. Now I've got ciphertext that only my private key can decrypt. And guess what? That's not going to be on my web server. That's going to be probably on a single system behind all my firewalls, safeguarded internally, because the only place I probably need to decrypt that credit card is to send it to my credit card processor. So let's look at what this does. So first I'll show you the code. I got neighbor mowing action going on here. Hopefully you can't hear all that. So I've got credit card, I encrypt. So you're on my site, you give a credit card. Here's the ciphertext. Again, now I can store this wherever I want, knowing that only someone who had the private key will be able to decrypt it. So somewhere inside my company, on the one system that needs to do the decryption, I take that data and I'll be able to decrypt it. But how that gets coded, pretty straightforward again. I've got the key. I'm going to do all that same, the actual encryption is what we saw before. This is all I need on the web server. Here's the public key. Again, I don't need to be concerned. It's public. If somebody owned my server, they'd be able to see my public key. The worst they can do to me is if they changed my, if they totally own my server, they could change that public key. Well, guess what? If you totally own my server, can dump memory and take credit cards as they come in, it doesn't matter, right? I've got other problems. So we've talked hashing, we've talked encryption. So now we're going to move into the next stage, digital signatures. So these, you want to be able to have contracts online, and I want to make sure that they have integrity, they haven't been modified, and I want non-repudiation, which just means if someone gives you a contract, you want to know that it hasn't been tampered with, and you can prove it came from them. That's what digital signatures will do. So we'll look at the picture. I'm going to mention here digital signatures by themselves don't need to care about confidentiality. So possibly you don't care if someone reads the stuff, you just don't want it to be modified. In my example, I just want to throw it all together and show you an example that pulls together everything we've seen. So I'm going to also do encrypting that data for confidentiality. So the picture will look very similar. You took your plain text, you take the receiver's public key, you do encryption. We saw this before, right? That's just the asymmetric encryption. You compute a hash of it. We saw that before. The new part here is I'm going to encrypt that hash with my private key as the sender, because that will become my digital signature. Why would I do that? I'm going to send you the ciphertext so no one can read it. This is a hash that's also been encrypted with my key. If you have my public key, you will be able to reverse and prove that that came from me. And once you do that, you'll have the hash so that you can make sure that after you do your decryption and such, things haven't been tampered with. So I get everything I want here. People can't read it, it can't be tampered with, and you can prove it came from me. The only way it wouldn't is if I had released my private key, which would be a big problem, obviously. So let's look at signatures. I'll show you how it would look on the web quick. So in this example, I just said I want to pass data to someone else via hyperlink. So maybe another vendor, I'm going to pass them. So I'm sending a secret here, my encrypted data. And if I were to go more to the right, you'd have my signature. So I just want to show you what this code would look like. It's going to be very similar to what we've seen with other segments before. So let's look at the sender here. Here I have the public key of the receiver and my public-private key. Again, don't just store it in a string. So let's look at the code. I need to create, I'm going to need my key. So I'm creating a cipher called sender cipher with my key. I need a receiver cipher. My screen just went blank here. Hold on. Been having some computer problems lately with that. All right. I take the receiver cipher with their public key. I take the credit card, and we'll see very similar things. Now I'm going to take the credit card plain text, and I'm going to convert it into a byte array. I'm going to encrypt it, so that's what we saw before with asymmetric. I can compute a hash like I did before. And then here's the new part, the signature formatter. I'm going to use SHA-512, and it will create a signature for me based on my private key. And then I can base 64 the ciphertext and the signature. So again, that's a lot of power and not a lot of code. I've just done something that no one can read. encrypted just for you, that you can tell hasn't been tampered with, that you know came from me. Where else do you see these things used? So I want to talk about the term is hybrid encryption. So I talked about symmetric is super fast, but we need to be able to distribute keys. Using asymmetric along with symmetric is what's called hybrid encryption, and a perfect example of it is HTTPS. So if you create a website, please use HTTPS. Regardless of what your site is, I can go on for that for an hour. But to do that, you need to create a public-private key pair, and you need to get it signed by what's called a certificate authority, like say Let's Encrypt. So the idea is I have a server, I'm going to create a public-private key pair. I want to take the public key, go to a certificate authority. They will digitally sign my public key. So they say, yes, Robert definitely owns this website. There's ways to prove it because I put a file in, etc. They'll give me back a certificate. What that certificate has is it has, here's the public key for this website, along with what domain it's attached to, and that it was signed by, in this case, Let's Encrypt. So this is using asymmetric encryption and digital signatures. So when a browser comes to your website, it's got what's called baked-in, well-known certificate authorities. So browsers know about Let's Encrypt and the major trusted certificate authorities. So when a browser comes to your site, it's going to say, hey, give me your server certificate. It'll take that server certificate. It will do the digital signature verification to prove that it was signed by Let's Encrypt. It says, I trust Let's Encrypt. So it pulls the public key out from the server. Then the browser says, I don't want to actually do encryption using asymmetric because it's slow. It chooses a random symmetric key on the fly. It encrypts that symmetric key using the server's public key. So now the server's the only person who can decrypt this, and it sends that to the web server. Now both the browser and the web server have a shared symmetric key, and it got there through digital signatures and asymmetric and trust and everything we talked about. Now when it does bulk encryption of all of your pages, it's just using symmetric, which is super fast, but it did the rest of that to prove that it was signed by the right people, and to be able to exchange that symmetric key safely. That's a good practical example of where this kind of comes together as well. I want to mention two things, key sizes. So there's a trade-off for performance and security. So if you look at symmetric AES, you could either use 128-bit or 256-bit. And if you think, well, the 256-bit is twice as good. So the way people attack AES, they're not going to, unless it's a poor implementation or AES gets broken, they're not going to break the algorithm. They're going to have to try to brute force guess your key. So the bigger your key space is, the harder it is for them to do this brute forcing. So if you do the math, 128-bit keys, 256 is not twice as hard. Every time you add a bit, it gets twice as hard. So using 256 is exponentially much more difficult than brute forcing 128 bits. My philosophy, I'm not going to get fired over a couple milliseconds difference by using 128 versus 256. So if you're concerned about perf, do what I would do. Set them up, run whatever you're going to run, do the 128-bit, the 256-bit. Should be negligible. If in your case it's not and you want to make that trade-off, use smaller keys. I'm going to use 256 because I don't want to get brute forced, because if I do, I'll probably get fired, right? So I just go for the largest key sizes personally. Same with asymmetric RSA, use 4096. So everything I've talked about before, now we talk about key storage. I said don't store it in a string and such. Key storage is the worst, right? How do you store a secret on a device that you feel someone can own? It's not a simple problem. It's the worst problem in my mind in cryptography. How did I get around it? Well, I got around it in the case where I did a public key and put it on the web server. Now I don't have a key that I care about there anymore. That's how I would deal with it. Credit card vendors have actually moved to where instead of you having your own public-private key, they'll create it on their side for each company, and they'll give you your own public key to use and not even give you the private because you don't need it, right? So you take the credit card, you use this public key. Now they're the only ones who can decrypt it, and you have no risk of it being decrypted in your own environment. Again, I get around the key storage problem that way. If you have to, depending on where you're deployed, maybe Azure Key Vault, some of the other options I won't get into, there's not a perfect solution, just to be honest with you. And you need to decide, how am I going to do this in the environment that I'm in? I gave some examples here. Hard-coded strings can be disassembled. ASP.NET in the web forms days had encrypted app settings, so you could actually encrypt sections of your ASP.NET config file using RSA encryption. And so you would be able to store it so people couldn't read it in your web config. The bad news is an ASP.NET page needs to get that, so when it asks for it out of the config file, it gets decrypted. So if someone was able to change your page, they're going to be able to get that decrypted too. Right? That's always going to be a risk. If you call another service to get a key, if someone can change your client and make that call, that's where the risks come in. So again, I don't have a lot more to say about that. It's a 101, and there really aren't a lot of great answers. Like I said, I try to avoid it by not storing secrets on my server. In summary, don't write your own cryptography. Use trusted algorithms and implementations. Make sure you understand what the goal is, and make sure you're using the right thing. So the thing I see most often is people confuse hashing and encryption. And they misuse the terms, they pick the wrong algorithms because they're not sure what they're trying to do. In the query string example, I didn't care if you saw it. I just don't want you to change it. That's integrity. Integrity should signal to you that hashing is what you want to use. Within encryption, you basically want to use symmetric because it's fast, and asymmetric can't do a lot of data, but you will have special needs like digital signatures, key exchange, where you may have to use asymmetric. And again, think through your threats. Don't just create something and think you're good and put it aside and be all proud of it. Think of it from the perspective of somebody attacking you. Like I said, when I did the capture the flag, it was eye-opening. I was shocked at how I thought differently and what I would look at and what I would choose to poke at and try to attack with. So as you do that and think through your threats, make sure you have proper countermeasures in place. I do have a Pluralsight course. It happens to be that Pluralsight's free all week. I think it ends tomorrow. So I've got a longer course, and that one's in .NET Full Framework. I didn't mention too much, but the framework and the full framework and the .NET Core, .NET 5 code is very similar. There's a few differences you'll see in just some of the class names and how you create instances, but for the bulk of it, it will be the same. I like this book, Practical Cryptography in Python. I've read it multiple times already. I don't know Python. It didn't matter. I was using it to see someone's practical recommendations on don't use MD5. I've heard that forever. Nobody explained to me why MD5 is broken. So it goes into how hashing works and what part is broken and why it matters at a level that's appropriate for me. I'm not into all the bit shifting. I don't care. With AES, I trust that people have looked at this. AES is implemented. I don't care how the registers and all the folding and all. I lose interest in that. If you're interested in that, these books here go into all of that kind of detail. I've read them all. Again, Applied Cryptography, Bruce Schneier's excellent cryptographer. I read the book not because I cared about how AES was implemented, but he talked about how you should use AES properly, like which modes to use and such. So that's what I got out of those. But if you really want to know how those algorithms work, those are some good books. If you're interested in the history of cryptography, how was Enigma broke? How did Caesar cipher start? Kind of the back and forth of attackers and how people respond. Both of these are good. The one is a huge book. I mean, you can read all the details and all the history if you're into that. I found them interesting myself. That's my Twitter. That's my blog. That's my email. That's the link for the slide and the code. Again, you'll have both .NET Full Framework and .NET 5 implementations. So if we have any questions people would like to run through.
I had one question.
Okay.
You said that storing things in strings is discouraged for storing things in binary, but shouldn't they be equivalent if you do it right?
I'll be careful what I said in case, so let me go back and show you what I was trying to say. I have a computer problem here. My display keeps going black, which is very disconcerting. What I'm trying to say is all of the algorithms here are built using byte arrays. That's how they all require a byte array as a parameter. We just all use strings. So there's just this disjoint. As a .NET developer, you've always used strings, and now you need to use this library, and you've got this weird disjoint of I need to encode it into bytes and get it back out. That's what I was trying to say. So I don't know if, does that make sense? So I'm not saying in the end, your string is in memory stored in zeros and ones, right? That's how it is. I'm just saying from a type perspective in C#, this has a string type, but I can't pass a string to compute hash. That's not what it takes as a parameter. It takes a byte array. So I just have to force it to be a byte array to be able to be used. And that's where that encoding to take it from string to bytes works. Does that make sense?
Yep, that makes sense.
Okay.
Did you say earlier that the .NET framework implements a lot of the core algorithms in the operating system? And if so, is that true of both the full framework and core?
Oh, I'll go back to that one. Let me go into the actual slides. So the suffixes that I talked about, it took a long time to find this when I was looking before. So let me get back to the slide. My display is not coming up here again. So what can you see the slide I've got with how .NET's implemented?
Not yet.
Okay, let me try to get that pulled up here again. How about that?
There we go.
Okay, so all I was saying is the classes have different suffixes. In the .NET framework world, these mattered. So the AES managed was written in C# and all IL code and didn't reference anything in the underlying Windows system. CNG ones use the cryptographic next generation, which is a certain version. It's the newer stuff built into Windows. Crypto service provider used the old crypto API. So it mattered, for instance, if you said, I need to write a .NET that's going to run on a super old XP or whatever, and all they had there was crypto service provider, and I needed to be FIPS compliant, you should pick AES crypto service provider, because that ticks all the things you need. If you needed to be FIPS, you couldn't be managed. And because you're on a super old version of Windows, this is the right suffix, because this will just be a wrapper for crypto API on Windows XP, for instance. In .NET Core and .NET 5, they still have all the classes with all the suffixes, so you don't have to change your code, but they're not meaningful anymore. They all wrap the OS libraries. So even though I used AES managed, it's really using whatever Windows gives me or the Mac uses or Linux. So when they implemented this on cross-platform, they looked at Mac and said, on Mac, these libraries come from this in the operating system. So they mapped manage to actually call into whatever the Mac has for built-in AES within Mac OS, and similar for Linux. Does that help answer?
Cool. Yeah, that's really interesting.
Okay.
Does anyone else have any questions? We've got Track Web. You can raise your hand or ask in the Discord.
And you may come up with some later, right, when you get the slides and the code. So feel free to reach out to me. I do a lot of talks, and you'd be shocked how little people ask later. So feel free. I put it up here because if you have a problem, I want you to ask. So if you want to reach out on any of those channels and say, I don't quite follow now that I've seen the code, why does it do that? Let me know.
Hi. I actually have a question.
Okay.
When you were talking about the RSA encryption, when you're just having the public key on the web servers and the private key elsewhere.
Yep.
Does that work with DPAPI?
So DPAPI is a built-in per machine encryption library in Windows, right? Just to get grounding, right? It figures out something specific to your machine. So if I were to encrypt it using DPAPI, it would be specific to the box I'm on. So if you were talking about when I was talking about web config encryption,
I think it was before that.
Okay.
Because I know,
I'll only say it in that one because web config encryption gave you both choices. You could use DP-API, but then it became a machine-specific config, which didn't work in a farm, right? So you wouldn't want to pick that. General, what I was showing with the RSA stuff. So let's go look at that example. When I showed, you have a website and you want to just put the public key on it.
Because I know with DP-API, you can, I know with Core, you can set it up to use a certificate. And that's how, for web farms, if a certificate and even like for the key storage, like a common location for the XML files to go. And I was wondering if it was possible that you could just have a single location for like the private key away from the web servers and just feed it public keys on the web servers.
So I got to see how I'll try to answer that two different ways. So by doing the technique I'm showing here, I'm distributing the public key on each physical web server. I could store it on a share or some other way or call a service to get it or whatever, but I don't want the front end to ever see what's truly a secret, right? That's the key for that part. What I was saying is I would only store that private key internally where almost no system, even on my corporate network, could get to it, right? If you're asking, so I'm trying to figure out how DP-API would play into that because DP-API will be machine specific. I've seen people say, for instance, I could do a symmetric key and use DP-API to protect it. I've seen schemes like that, right? Where somebody says, I'm going to make up a symmetric key to use, but I want to use the local DP-API on my machine to encrypt it. You could do that. The problem is your code has to be able to get the symmetric key in that case, right? So code has to be able to, and this is why I say services aren't great either, right? Yeah. People dream up, let's write a service over here, and you can call the service and it'll give you the symmetric key to use. Well, that's great, but if I own your box, I can call your service too. Right? I need that key to do the encryption, and that's where your leak would be. If you ever see a secret key on your front end, regardless of where it was stored or how you got it or how great that is, you eventually have a way as a developer to get that secret key, unless there's hardware modules and everything else. Unless you are taken away from the ability to ever see that key, you're still going to be part of the problem, and I don't want that key exposure. And that's why the public makes sense, because you would never have that case, right? You never get where public key is actually seen to you.
Gotcha. That makes sense.
Okay.
Because I was just thinking in terms of, when it comes to cookies and session cookies on a farm, you have to use DP-API in order for all of those session states to be for it to be able to read and store between. And I'm wondering if the way you're doing it here, could be an even better way.
Yeah, so if you're getting like, if you're a web server and you want to issue a session and you want it to be somehow opaque or encrypted, right, when it goes to the client and ends up in a cookie and it gets retransmitted and all those other things. Whether or not you can't use truly what I would call sounds like old school DP-API where it was machine specific. I suppose you could still do that because in your farm, you're probably routing them back to the same web server, right? Yeah. In which case you'd be able to get that decrypt out. And whether or not doing this makes more sense to me, the problem is regardless of how I encrypt that session key, I have to use HTTPS to protect it. Once you have it in that cookie in the end and it gets retransmitted, honestly, whether that's encrypted or not doesn't really matter. I'm taking whatever that session key's value is and using it, right? So someone on the other end, as long as they can get the value, whether that's an encrypted value or not, right, can still issue to me and I'm still going to use it, if that makes sense.
Yeah, that does. Thank you.
Yeah.
Thank you so much, Robert. Really appreciate your time.
You're welcome.